I just wanted to take a little bit of time to highlight a couple of important pieces of the electricity notes. So when we're talking about electricity, we have some vocabulary that is most likely new to you. So we want to make sure that you take some time to look over the new vocabulary words, make sure that you understand what it is that they mean, and get familiar with the variables and the units for each of those variables. So voltage is basically a vocabulary word that means that we have some difference in the amount of electrical potential energy between two different places. As long as there is a difference in potential energy, then the electric charges are going to move in an attempt to balance those charges. But what ends up happening is that it creates a flow of moving electrons as they move from an area of high potential energy to low potential energy. And in doing so, those moving electrons essentially create electricity or a current flowing electrons. So voltage is the reason that these electric charges move. It's going to be measured in volts. So voltage is measured in volts. And a volt is the ratio of energy per coulomb of charge. Now, a coulomb is a unit for measuring bundles of charge. So if you think back to chemistry, whenever you were talking about molecules and molarity and things like that, you had a mole, which was a unit that meant that you had a whole bunch of molecules, but collectively they took this bundle and they called it a mole, right? So whenever we're talking about a coulomb of charge, it's that same idea. It's a bundle of electric charges or a bundle of electrons, okay? So a volt is the ratio of energy per coulomb of charge. So voltage sources can be lots of different things. It's basically anything that provides that electrical potential energy difference that causes those electrons to move. So a battery is a very common source of a voltage source. And you can see from this illustration, these little images that look like men would represent our bundle of electric charges or our coulombs of charge. And then the cups that they're carrying are bringing energy. So a voltage source is anything that has that electrical potential difference, and it is where that energy or the reason why that energy gets carried as those electrons move through the circuit. In this particular illustration, you see that they have one light bulb to light. So they're taking all of their energy and dumping it into that single light bulb. As they come out of the light bulb, those cups of energy are empty. So we say that our voltage is going to drop or decrease as the electrons move through the circuit. So from this illustration, you can see that coming out of the positive end of the battery, we have 1.5 volts available, but then after the charges go through that light bulb, we are down to 0. So the value of energy available per coulomb has decreased. So we sometimes call this a voltage drop. Each device is going to use up some of that electric energy, and so the amount of voltage is going to drop little by little as the electrons move through the circuit, and eventually all of the energy will be used up, and we always have our electric charges returning back to the battery with 0 volts left over. And now, how much voltage does each device use? That depends on the devices, but always the electrons will leave the voltage source with all of the voltage available and return with 0 left over, okay? This illustration is just trying to show you how if we have multiple devices on a single circuit, then the energy is going to have to be provided to both or all, however many there are. So each device will get a portion of the voltage available. How much it receives will depend, again, on the device. If they're identical devices, then they would each get half, but if they were not identical devices, then they would each get some, but collectively they would use up all of the voltage available, okay? So no matter how many bulbs or resistors or devices are present, all of the voltage must be used in the circuit. Current is another vocabulary word and variable. So current is going to be represented with the letter I in your formula. And this is the rate of flow of the electric charges. So current is basically how fast those electrons are moving through the circuit, okay? It's going to be measured in a unit called amperes, which most people just call amps for short, and we will write that with a capital A as our unit if we don't write out the word amp. All right, so our charges are always going to go from the positive end of the battery to the negative end of the battery. And remember that those currents, those electrons or that current does not flow unless there is an electrical potential difference, okay? All right, just a little bit of trivia that may come up in the future. Remember that electrons are just parts of an atom, so make sure that you understand that the batteries do not provide those electrons. Those electrons are already present in the atoms that make up the wiring. It just simply provides the reason for those electrons to move. We can measure current by taking the electric charge and dividing it by the time. So basically, if we go back to thinking just in general that speed or velocity is distance over time, in this case, it's going to be the amount of charge that flows by per unit of time. The lowercase q is our symbol for electric charge. Capital C is the symbol for the unit coulomb. Okay, and I've already addressed what that is. Make sure that you know the difference between conductors and insulators, and you can go back and look through the notes to read that and see what the difference is, but you will be expected to know conductors versus insulators. All right, types of current, basically how are the charges moving and what direction and why. So a direct current is where your electric charges are going to move in the same direction the entire time. Voltage sources like a battery have a designated positive and negative or high and low voltage location, and so the electrons are always going to flow following the same path, same pattern, same direction through the current because the positive and negative ends of the voltage source are set. Alternating currents would be things like outlets in your home. And what happens with the wall plugs or alternating currents is that the polarity, in other words, where the positive and the negative charges sit, where the high and low charge values are located in the wall, actually changes. So the electrons are always going to go from high voltage to low voltage. So as the polarity changes, the direction through the wire that the electrons are moving will change accordingly. So it's called an alternating current or an AC current because the electrons do that. They alternate their direction, go back and forth, back and forth. Home outlets are typically 120 volts, and please take some time to review fuses and circuit breakers to make sure you understand the purpose and how they work. Resistance is another variable for us, and so this is going to be measured in something that we call ohms. You can think of like a meditating person if that helps you understand how to pronounce it, but an ohm is the unit for measuring resistance. And so similar to the idea of friction, resistance is going to oppose or make it difficult for those electric charges to move. So all of our devices are going to provide resistance. If you think of the electrons trying to move through the wire, they have to maneuver through that device, and so that is going to slow down the rate of the flow of those electrons. The more devices it has to go through, the more resistance it experiences. This illustration on this slide is just showing you that as resistance increases, the current decreases accordingly. Resistance is affected by the length, diameter, and temperature of the device or whatever that resistance is coming from. We do have things called resistance wires that are, it may not be an electrical device that turns on or off, but it's some sort of device or maybe just a segment of the wire that has been designed to provide resistance to slow the flow of the electric charge. And you can see here how specifically the length, diameter, and temperature affect the resistance value. This is our primary formula for this chapter. Ohm's law is the equation V equals IR, where V stands for the voltage measured in volts, I stands for the current measured in amps, and R stands for the resistance measured in ohms. You will be asked to answer questions using this formula. So once again, make sure that you take time to get familiar with the variables and the units that go with each of these. Power is going to be the same power that we discussed before when we talked about our work energy power unit. At that time, we said that power was the rate at which work was done, and so it was joules per second. Well, it's exactly the same thing now. It is still energy in joules per second. So power is joules per second. And just like before, we're going to measure this in a unit called watts. And our formula for this chapter regarding power is P equals IV, where you can calculate the power used by multiplying the current times the voltage. If you would like, you can go to YouTube and you can watch an episode of the Magic School Bus over electricity. It is called Magic School Bus Gets Charged. The full episode should be about 30 minutes long, and this is just kind of a fun, really simplistic intro to the idea of electric circuits. You are going to be expected to understand what it takes to allow those electrons to flow through a circuit, and you're also going to be asked to know the difference between series and parallel circuits and how those setups are going to affect the different variables that we just looked at, as well as in general some conceptual things about how the circuits perform differently because of the different setups. So feel free to go and give this a look if you'd like, just for fun, a little bit of maybe throwback to your childhood as well. I hope this was helpful. You guys have a wonderful day.